In these videos, we're going to look at forces of motion, mainly Newton's first, second, and third laws of motion. So you should have some notes that accompany this, which you want to make sure you read through first, so you're okay with all the lingo. And then you should have your example sheet ready with the questions on that we're going to look at. We'll start with question 1, obviously. These should be quite quick to start with, just to get used to the jargon that's associated with this topic. So a block of weight W is being pulled to the right by a force P across a rough horizontal plane. Draw a force diagram to show all the forces acting on the block. So rough horizontal plane, the fact that it's rough means that there is friction. If it's smooth, then you ignore that there might be friction. So here's our block. It's got weight W, so if it's weight W, the weight acts directly down through the center of the block. So our weight's going to go down here like this. And also we always have a normal reaction force, which always acts perpendicular to the plane. Okay, so the reaction force we call R, the weight we'll call W, so it looks like this. We'll talk more about these kind of forces as we look at more questions as well. But the reaction plane is always at 90 degrees to the plane. So if the plane is, say, like this, then the reaction force will be going this way at 90 degrees to it. But we'll come on to them later. And the block is being pulled here along this plane. So we've got the pulling force, okay, which we can call P. So pulling it from left to right, and then acting against that, we will have friction because it's a rough plane. So there's our diagram representing all the forces acting on the block. That's number 1. So number 2, we've got a diagram showing the force acting on a particle. Draw a force diagram to represent the resultant force, and then describe the motion of the particle. So if we just quickly have a little look at drawing this out, so we've got our particle. Oops. And we've got 4 forces acting on it. We've got 30 newtons going up, 10 newtons going down. Don't worry, it doesn't have to be length to scale or anything. Okay, the values are the most important thing. And then we've got 20 newtons each way. Get rid of the ruler. So it looks like this. So the resultant force, so if you look at this diagram, we should be able to see that the horizontally, if we look at the horizontal forces and the vertical forces separately, we've got 20 newtons here going to the right and 20 newtons going to the left. So there's going to be no horizontal movement here because these forces are identical and they kind of balance each other out. So it's not going to move horizontally at all. But hopefully we can see from our vertical forces, we've got a much bigger force acting upwards than downwards. So the result of this is the particle is going to have a resultant force acting upwards on it. So our resultant force will be 20 newtons upwards, because 30 upwards, 10 down. So 30 minus 10. We'll have a 20 newton force acting upwards on our particle. So that's our diagram. Part B, describe the motion of the particle. Well, if there's a force acting upwards, then the particle is accelerating upwards. And that's its motion. Okay, we'll come on to more about acceleration and mass later on in this topic as well. So there's question 2. So hopefully we're getting kind of more used to what these forces, how you can write them, how you can draw them, what they mean. Number 3, so we can also explain forces in vectors I and j, which you've come across. I being the horizontal vector this way, and j being vertical vector up. If you introduce a third dimension, then we normally use k, but we don't have to worry about that here. So the force is 2i plus 3j, and they're vectors, so we've got them in bold or underlined in our case. 4i minus j and minus 3i plus 2j, and ai plus b lots of j act on an object which is in equilibrium. So it's an equilibrium, all the forces acting are balanced. So we should be able to form an equation here and use that. So if they're in equilibrium, that means our resultant force, so if we add them all together, remember if we add vectors together, we get the resultant vector. Okay, in this case, there is no resultant vector. The object is not going anywhere. And then we can match up all the i's, match up all the j's, and we should be able to find a and b. So we've got 2i plus 4i is 6i, minus 3i is 3i, plus ai, so they're my i's. And then j's, I've got 3 minus 1 is 2, plus 2 is 4. So I've got 4j plus b, j, and we know that both of these equal 0 because there should be 0i plus 0j effectively on this side. Then we can just look at the coefficients, so 3 plus a is 0, and then 4 plus b is 0, so a will be minus 3, and b will be minus 4. Okay, so it's in equilibrium, there's no resultant force acting, the particle is not moving in any particular direction, so there's no I movement, there's no horizontal movement, there's no j movement, there's no vertical movement. So all the forces must balance up and down, left and right, just like in question 2, where we've got these forces here balanced, so this particle is not moving left or right at all. Question 4. A particle begins at rest at the origin. It is acted upon by 3 forces, 2i plus j. So we're looking at force in the same kind of way here. Newton's 3i minus 2j. And minus I plus 4j, all in newtons. Find the resultant force in this form. So the resultant force is just an accumulation of all our forces. So if we add them all together, just like with vectors, the result of applying all these forces will be 2i plus 3i, 5i minus 1 is 4i, j minus 2j plus 4j is 4j as well. So that will be our resultant vector or resultant force. Oh no, hold on, sorry, should be 3, shouldn't it? 1 minus 1 plus 4 is 3. Part B. Work out the magnitude and bearing of the resultant force. So if we think about this particular combination of vectors, 4i plus 3j, sorry, that means our particle is starting here. It's being acted on by a horizontal force of 4 and a vertical force of 3. So it's kind of going off in this direction, because that's the resultant force that's acting on it. So we can work out the magnitude. So the magnitude, hopefully you can think about this yourself. So the magnitude will be the distance, the absolute value of the vector. So it's going to be x here. We can use Pythagoras to find the magnitude of it. And the bearing, remember, bearings are measured clockwise from north and consist of 3 digits. So our bearing that it's heading off in, if we put our north line in clockwise from north, that angle there, theta, will be our bearing. So let's do them separately. So our magnitude by Pythagoras, x squared is 3 squared plus 4 squared. So x is the square root. If we just do it all in one go, you'll get better at doing this and quicker. You shouldn't need to write everything out. So we get x is the square root of 9 plus 16. So root 25. So the magnitude of the vector is 5 newtons. Everything's in newtons. And the bearing, if we look at our right angle triangle, we can work out alpha using tan. So tan theta is opposite over adjacent. Or tan alpha is opposite 3 over adjacent 4. Take the inverse tan of both sides and you get 36.9 degrees to 1 decimal place. And therefore the bearing of this resultant force will be 90 minus this. Okay, we shouldn't round this here. I don't have my calculator on me. But yeah, it's going to be 53.1. And because it's a bearing, we should put the 0 at the start. And then finally, part C. Describe the motion of the particle. So the particle accelerates in the direction of the resultant force. So the particle's heading off in a kind of northeasterly direction. So you could be a bit more specific here and say it's the resultant force of 5 newtons causes, on a bearing of 053.1, causes the particle to accelerate in that direction. We've kind of got all that information there. And that's the next one, that's question 4. We'll stop this video here, and then I'll start a new one for question 5 onwards.